Hi and welcome to High School Physics Explained, and today I'm going to go through the answers of the HSC Physics paper of 2019 for Module 6, which is the Electromagnetism section. And again, like I did for my Advanced Mechanics video, then if you are not part of New South Wales curriculum, it's still worthwhile watching and looking at the questions that I go through today, because the topic is really just electromagnetism, which looks at motor effect and induction and so forth. So it's really applicable to many situations around the world. So let's get started. This is question number 5 in the paper. The diagram shows two coils wound around a solid iron core. Initially the switch is closed. Opening the switch will cause the galvanometer pointer to A, remain constant reading, B, move from a non-zero reading to a zero reading, C, zero reading to a non-zero reading where it remains, and then finally moving from a zero reading to a non-zero reading and then back to zero again. Before we look at that, make sure you have a good understanding of what's going on here. So the switch is closed. Let's describe what's going on. So we have a current flowing through here, and using the right hand grip rule, you're going to get a current that is heading in the direction like so. That means this is acting like an electromagnet, and using this metal rod, we've got greater flux linkage. So what we have is a really nice, strong magnetic field. I'm going to just sort of draw like so. Now, because this current is going in that direction, this is going to be a north pole over here. But as long as the switch is closed, this magnetic flux lines here don't move. They're not changing. Although these wires here are experiencing a flux, they're not experiencing a changing flux. Faraday's law says the EMF is equal to negative delta phi over T. That is the rate of change of flux. Since these flux lines aren't moving, we're going to have a value on the galvanometer, initially at least, is going to be equal to zero. Nothing's going to happen. What happens though when the switch is open? Well, that means this current's going to stop, but it's not instantaneously gone. These lines will start to collapse. That means they're going to get smaller, which means we're going to get a changing flux. So the galvanometer reading will actually not be zero, experiencing a changing flux. Once the current has completely dropped off, there's going to be no magnetic flux lines there at all, which means my galvanometer is going to go back to zero. So as a result, looking at all those responses, you can see that the only correct answer is going to be D. Question number 7. We've got a bar magnet is moving away from a stationary coil, and which diagram correctly shows the direction of the induced current in the coil and the resulting magnetic polarity of the coil. Now, our responses here are all diagrams, so it's really important to look at them very closely. That is, you can see we've got north for A and B here, and south here. Secondly, we've got arrows going up here, down here, up here, and down here. Here we have a south-north and a south-north, both heading from left to right, and here we also have the south-north and south-north heading from left to right. Now, with that in mind, let's see what this question is trying to ask. It says, well, what's going to show the indirection of the induced current? Now, the induced current is due to the changing magnetic flux, which we just discussed, but the induced current has a direction such that it causes a polarity of poles such that it opposes the motion. So if this is going to move in this direction, we want Lenz's law at play here, so that we are going to have the south pole moving away. We want a north pole being developed here at this end if we want this to oppose this motion. Now this diagram automatically says north is over here, so automatically A is wrong. Here it's the same story. We have a north over here, but we have this south wanting to move away. We want to generate a north pole, which is going to cause it to come back again, that is oppose the motion. So this again is correct. So here we correctly see we have a north pole here and a north pole here. So our answers are now restricted to C and D. But the question now is which is showing the correct direction of the current. And using your right hand grip rule, that is, you hold the coils here with your fingers heading in the direction of the current, your thumb is going to point in the direction of the north pole. Now, the only diagram here that fits that bill is D. So it is, my fingers curl down, which my thumb therefore causes pointing towards this end. So the answer is D. Question 17. Now this one takes a little bit more detail too. We've got a straight line current carrying conductor XR and is connected to a battery, and a variable resistor XR is enclosed in an evacuated chamber with a fluorescent screen at one end. And a cathode ray enters this chamber directly above Q, initially traveling at a parallel to QR. It passes through the chamber and strikes the fluorescent screen, causing a bright spot. And then which direction will the spot move towards if the resistance is increased? There's a lot of factors here. First thing, again, is to label what you know. So we've got a cathode ray, and that's going to go all the way like so, and it's going to give us a nice little bright spot right here. So what we in essence have is a flow of negatively charged particles or electrons going from here to there. In essence, it's a current. But the conventional direction of this current is going to be in that direction because it is always in the opposite direction of the electron flow. So this cathode ray has a conventional current direction of heading in that direction. Why is that important? Well, now we have two currents that are side by side, and Ampere's law says that these two will attract or repel depending on the directions of the currents. Now, based on our diagram, we can see here, this is the positive terminal. We know that the direction of the conventional current is going to be from Q to R. So now what we have is two beams or two lines of current, but they're in opposite directions. So these guys would naturally repel. So actually this dot wouldn't be sitting here, it'll probably be sitting more likely up here, because as it moves down here, it's being repelled by the one above it. But then, at an extra level of complexity, we're told that the resistance is increased. So if the resistance is increased, then the current in QR is going to decrease. And since the formula for the force over the length is proportional to the individual currents divided by the distance between them, then the force is going to weaken. So this spot is going to move downwards as the current decreases because the resistance is increasing. So therefore, the only possible answer is it's going to move towards Z, and D is our answer. Question number 18. A circular loop of wires connected to a battery and a lamp apparatuses move from P to Q along the path shown at a constant velocity through a region containing a uniform magnetic field. And we're having to see what happens to the brightness of the lamp as it moves through. Now, again, there's lots of layers, and that means it's a more difficult question. Question 18, 19, and 20 are usually the more difficult questions in the paper. But there's a lot of things here. You've seen diagrams where a loop of wire moves into a magnetic field that causes a change of flux, and that means an induction taking place in the loop of wire. But this has also already got a current. So let's just ignore the current just for the moment and ask ourselves what happens as it enters as a ring. So if we have no current here, what we have is as this moves in here, that we will generate an EMF. Now, what is the direction of the EMF as we enter it? So it's going to create an EMF that opposes the motion. So that is, as we go in that direction, we're going to have an EMF that opposes it. So that means we're going to produce a current that is in that direction. Right? Now, again, I'm just ignoring my polarity for my lamps here. As it leaves, it's going to do it exactly in the opposite direction. So it's going to generate an EMF in that direction. Now, this has already an EMF due to our battery. So since we're getting an oppositional EMF here, because this causes a current in that direction, right? This is a current in that direction. We have an opposition in that direction. What we're in essence going to get is we're going to get a drop initially in lamp brightness as it enters. As it goes in and stays in, we don't have a changing flux, so we have no EMF in the middle, and so the brightness is going to go up again a little bit. Then what we're going to get here, we're going to get an EMF that is generated, but this time it's in the same direction. So it's now going to increase. In fact, it's going to get the lamp even brighter than it was before until it leaves again. So B is our best response. Notice it's bright due to the inherent battery. Because of the opposing EMF generated, we're going to get a drop in brightness. And as it passes through the center part of the magnetic field lines, it's going to go back to normal. But now as it starts to leave, it's increasing its EMF because now we're getting EMF generated in the same direction. So it's going to be much brighter. And then once it leaves, it'll go back down to flat. And therefore B is our answer. We're beyond the multiple choice, and now we're going into the short answer responses. Like all questions, being 7 marks, it has 2 parts going through it, and we need to read the question carefully. It says a step-up transformer is constructed using a solid iron core. The coils are made using copper wires of different thicknesses as shown. See that this is definitely different to that side. And then we have a table that shows the electrical data for this transformer. And then we're asked 2 questions. Explain how the operation of this transformer remains consistent with the law of conservation of energy, and include a relevant calculation in your answer. And B, explain how 2 modifications to this transformer would improve its efficiency. Now, notice that both questions are explain questions. So to get full marks here, you need to more than just identify modifications. You need more just identifying or how this is consistent with the law of conservation of energy. You need to explain, that is cause and effect. If conservation of energy says that the energy going in has to be equal to the energy going out, that means also the power input has to be generally equal, or it can be dropping like so to the power out. So now let's have a look at our data. We've got our secondary voltage and our secondary current, and here we've got our primary current and primary voltage here combined. So this is our power input, 500 joules per second or 500 watts. Now what is our power output? Well, that's equal to also VI. In this case we've got 450 watts. So our output here is 450 watts. It's less than the input. Now that's not surprising. We have a solid iron core, and so this solid iron core, although that establishes greater flux linkage for this transformer, we're going to have production of lots of eddy currents in this soft iron core, which means we're going to lose some power. So this is consistent with the conservation of energy. The power input is definitely not smaller than the power output, and so therefore we're going to see that this is consistent with the conservation of energy. Okay, the second part of the question says explain how 2 modifications to this transformer would improve its efficiency. So what we want to do is we want to reduce the 50 loss that we're getting here through eddy currents. Well, the first clue is we've got a solid iron core. So what we can do is we can laminate that iron core. Now laminating the iron core, meaning that it's got layers, we are reducing the size of the eddy currents, and therefore reduction of eddy currents means reduction of heat loss due to the generation of those eddy currents. Now that's not the only place where we're going to lose energy. We also have these thin wires here, and thin wires means higher resistance, so more loss of energy in terms of heat. So by thickening up these particular wires like so, we're going to have the ability to have high currents entering our transformer here, and as a result less energy loss. So those are 2 modifications, and I've explained why those modifications have resulted in increased efficiency. Question 28. We've got a metal loop WXYZ connected to a battery and placed in a uniform magnetic field, and a current flows through the loop in the direction as shown. And the loop is then allowed to rotate by 90 degrees about the axis, and we're looking to compare the forces acting on WX and XY before and after. Now that means you need to make sure you look at both befores and both afterwards. So one way you can do this is set up a table. So if we wanted to set this up a table, I might put WX over here and put XY over here, and then look at the before and then look at the after. Let's go through it. We know that this wire of WX has got a current in that direction, and it is at a maximum. The current is perpendicular to the magnetic field lines. So according to F is equal to BIL, we have a large force. And let's say we call this force a value of F in that direction. What about x, y? Well, now what we have is our y is traveling parallel to the magnetic fields, so our force is going to be equal to 0 because you need to have the y perpendicular to the magnetic field lines. But that's not enough. What happens if this turns 90 degrees? Now that means our Wx is sitting, let's say, above here. I guess if I were to get you to visualize this, this is sitting sort of like closer towards you as this bends out like so. Wx is still perpendicular to the magnetic field lines. So we're still going to get a value f, but in this case the value of f for the first one is heading in that direction, that is down. But the second one is still the same. It's still experiencing a force in the downward direction. But now, xy is now perpendicular to this, so it's coming in and out of the page, so to speak. It is now perpendicular to the magnetic field line, so it is experiencing a force. So the value is actually equal to F. But in this case, because of the way that you orientate your hand, the force is now going to be going, in this case, towards the left. Now, if you were to have this rotate in the opposite direction, then of course you might find that this force then goes towards the right. But in any case, we're now comparing the forces. It has a force, it has no force. This one has a force, it's the same force, but now this experiences a force as well. Question 29. We have a particle of having mass m and q, and it's accelerated from rest through a potential difference of v. Assuming that the only forces acting on the particle is due to the electric field associated with this potential difference. And then we're asked to show that the final velocity is given by this formula. In essence, what we're asked to do here is derive the formula from basic principles. In order to do that, we have a particle of mass and a charge q. It's accelerated from rest. Now, what does a voltage difference do? It gives the object an increase of kinetic energy. That is, the work done is going to be equal to an increase, in this case, of its kinetic energy, which is half mv squared, and the work done is equal to qv. So there is the basis of this question. If I now clean this up, I'm going to get v squared by itself, and I'm going to get 2qv on one side, and I'm going to get m on the bottom. So v now becomes the square root of 2qv over m, and hey presto, there is the answer. The thing here to pick here is that you will learn lots of formula from other areas that aren't on your formula sheets. It's important to see where they come from. So here's a good example where a formula is a result of an understanding of the physics principles behind that formula. This question, we have a question of a fan spinning and a spring balance is attached to the fan. And we're asked, first of all, explain the changes that would be observed on the spring balance in the first 15 seconds after the fan is switched on. Now it says 15 seconds here, so we're told that it reaches maximum velocity after 10 seconds. Explain the changes, so we're going to go cause and effect. So initially, we're going to have a value on the spring balance here that is going to be a value due to its weight. So therefore, at t is equal to 0, we can say that the spring balance is going to be equal, let's say, I'm going to say, just say the spring balance here is going to give us its weight, which is the mg. It then starts to speed up. Now that means as it speeds up, this is pushing air down, the blades of the fan is pushing the air down, and as a result of Newton's third law, the value of the force onto the blades is going to go in the opposite direction. So I'm now explaining that Newton's third law is applying a force onto the blades due to the fact that it's pushing the air down. So now what we have here on the spring balance, we have two forces acting. We have the force of the weight of the fan, but we now also have the force of the air on the fan. So there's Newton's second law here, which simply says that the acceleration is determined by the mass and the net force. In other words, the spring balance is now going to go smaller. So the spring balance is now going to read something smaller than mg because it's basically getting the sum of the forces to do with the air plus the force to do with the weight. So now we have a value that is going to be less. Now that's going to continue to rise as it speeds up for the first 10 seconds from 0 to 10. But then after 10 seconds to 15, it's reached operational speed, maximum rotational speed. So now what we're going to have is that this reading will stay constant. So the spring balance will have a value that is going to be constant. So here it's decreasing, and here it's going to be constant again, but at a value that is less than mg. We've talked about the fact here, I've explained why at t0 it's mg, why it's decreasing from 0 to 10, and why it again remains constant here. And this, of course, we need to tie in with Newton's first law, because now the net forces here are equal to 0, and therefore it's not accelerating upwards anymore. Should give you the complete formula for Marx. Before I move on to part B, one might say, well, hold on, this is not about to do with electromagnetism. No, that's true, but these are basic physics principles. So this question, even though it will address electromagnetism in the second half of the question, requires you also to have a good understanding of foundational physics, in this case, Newton's 3 laws. The student predicted that the current through the fan's motor would vary as shown on the graph. Assess the accuracy. Well, if we assess the accuracy straight away, this is incorrect. The fact is that as time increases and this spins faster and faster and faster, we're going to get more back EMF. And more back EMF will mean that we're going to get a current that is going to decrease. So let's talk about back EMF. Well, we have a motor here that's spinning in a magnetic field, which means you're going to get a generation of an EMF that opposes the one that generates it. So we're going to get a drop in voltage. So let's say the fan is connected to a 240 volt power supply. So it may say 240 volts. Then as it starts to speed up, so that's at time equals to 0. Let's say as a time to speed up, let's say it's going from 0 to 10 again, we're going to see a drop in voltage. Why? Because the back EMF will reduce this amount. Then eventually, beyond the 10 seconds, reaching opposite speeds, it will actually now be stabilized, and it may, let's say, and I'm going to choose a value, it may stabilize at around 200 volts due to the fact that it's still spinning and it's providing a general back EMF value of approximately 40 volts. So that's going to be stable. So in other words, you're going to get a value of the current. Of course, current is proportional to the voltage, okay, with the resistance, of course, on the bottom. So the current is going to go down, and then, of course, it's going to level out after 10 seconds. And that should be the correct value after that. Question 33, which is the last of our electromagnetism questions in this paper. We've got two charged particles entering the field from opposite directions, and we're asking to explain one similarity and one difference in their trajectories as they move into the magnetic fields. Now, if we're going to describe the details, we know that this particle here has a mass of m, then this particle here, the alpha particle, will have a mass of 4m because an alpha particle is a helium nucleus, which is 4 nucleons, 2 protons and 2 neutrons, and roughly speaking, that's going to be 4m. The charge in the proton, which is going to be a value of +1, and the charge of the alpha particle, of course, is +2. That is, it's missing 2 electrons to make it a helium atom. Therefore, we have two positively charged particles entering the field, and therefore their trajectories are going to change due to the idea of centripetal force. And that centripetal force, mv²/r, is going to be provided by the fact that it's got a charge moving at a velocity and a magnetic field. Because this force is always perpendicular to its motion, these two particles will start to turn. So we know this guy is going to turn this way, and this guy is going to turn this way. And that is already one big difference. That is, one is going to flick up and one's going to flick down. But I think we need more than that. But we can discuss explaining one similarity. They will both go a circular path because of the fact that they will experience a force that is perpendicular to their velocity, and therefore that results in a circular path. but their difference in their trajectories needs to be examined using this formula. If I rearrange this, I'm going to get r is going to be equal to mv squared over qvb. Now cleaning that up, you can see I'm going to get an mv up the top and I'm going to get qb on the bottom. So the radius is determined by the charge and the mass. Now for the proton, if r is going to be simply equal to mv over qb and m is going to be the value of, let's say, 1 and q is going to be the value of 1, then the r for the proton is going to be equal to 1 multiplied by v over 1 multiplied by b, and so it's going to be equal to v over b. Now I'm just using the values of 1 for both mass and charge here. But what about the alpha particle? Well, the alpha particle has a mass of 4m, so what we have here is 4 times v, but the charge here is going to be equal to 2qb. Now that q's gone, and so what we get in there is 2v over, this is an r by the way, over b. So in other words, its radius is twice as big to that of the proton. So that we're saying is that if this turns a circular path, this has to be 2r and this has to be 1r, simply because of the fact that it's 4 times more massive and twice as much charge as our proton. So that's one difference and one similarity explained. And so that was electromagnetism, and at least the questions from the 2019 paper that dealt with electromagnetism. And I hope that's helped you. In my next video, I'm going to look at the questions and answers for the section on what is light, or module 7. Now, a little competition here. I have a t-shirt here that is somehow related to electromagnetism. If you can give me the best description as to how this is related to the topic, then I'll give you a great big shout out and in my next video. So just put your answers in the comments below. Anyway, I'm Paul from HSC Physics Explained. Take care. Bye for now.